So hello, good afternoon, everybody, and welcome to our EPIC online technology meeting on photonics for the mobility of the future. My name is Antonio Castelo. I'm technology manager at EPIC, and today we have 6 nice presentations about different photonics technologies related with the future of automotive and the mobility markets. So we will talk about LiDAR, about monitoring, about laser welding, and other different topics related. But let me first say a few words about EPIC, in case you don't know us yet. EPIC is the European Photonics Industry Consortium. We are the world's largest association in the field of photonics. And you can see in this slide, we reached this year the impressive number of 800 corporate members. Our goal is to guarantee the sustainable development of the photonics business in Europe. In this slide, we are showing the great EPIC team, which allows us to be active in very different areas. We organize technical workshops and roundtables, offering to our members a highly valuable network to find different options for collaboration and to generate new business opportunities. We also provide market analysis and reports to help our members to learn about new possibilities for their companies. We offer the possibility of finding the right investor for each company and market, and we also support human resources activities with the Job in Photonics website. This is a list of the events we have planned for the next months. We always encourage you to go to our website, where you will find all the information and dates. Today, I just want to summarize a few of them that are interesting. First, the 2 delegation trips to Israel and Singapore. In case you're interested in increase your business in those countries, I think it's a good opportunity to join our delegation. Very interesting also the technology meeting we will have on electronics and photonics in Munich in mid-November. Most of you are involved in those 2 topics, so it's a great opportunity to meet with a lot of people in the same field. And finally, a couple of online technology meetings in early 2023. One about of metamaterials and meta lenses, and the second one related with laser manufacturing of implants. I also highlighted a couple of them in green because we are also organizing not only technical meetings, but also general meetings to help our members to learn more about the business, the situation of the market, and different topics that are more general and not only related with technology. For example, in October 28, we will have the international delegation trips to show everybody what is expected from those trips and what's our idea behind that. And in mid-December, we have the investor workshop. So everybody interested can join us and learn how to reach investors, how to work with them, and what's the best way to propose them the solutions to get money for your company. The event today about photonics and mobility in the future is supported by 3 fantastic sponsors. First of all, the company phix, that offers assembly services and contract manufacturing for photonic integrated circuits and MEMS. I don't know if we have Jerome from phix over here. I don't see him connected. So well, thank you to phix. Anyway, we also have the sponsorship of ficontec, an innovative high-tech company, a market leader in automated assembly and testing of optoelectronic components and hybrid photonic devices. And last but not least, we have Acktar, world leader in high light absorption materials. We have Alexander here, so you have the room to say a few words about your company.
Thank you, Antonio. My name is Alexander Telle. I am the CEO of Acktar's German subsidiary. Acktar itself, it's an Israel-based technology company, and we do ultra-black coatings and coated foils to suppress scattered light in optical systems and photonic instruments. And also for like the mobility sector, there are a lot of applications that need stray light suppression absorbing coatings like in LiDARs or any other sensor that make autonomous driving possible. But also in the manufacturing technology behind, like in laser production machines, there are our coatings used, for example, to beam dump lasers and to make beam quality possible.
Thank you, Alexander, and thank you for your support as well. And finally, we have for the organization of this event the collaboration of AILU, the Association of Industrial Lasers. Unfortunately, Mr. Dave McClellan, that is the executive director, cannot be present today, but we have Paola de Bono. She's going to be one of the speakers today, and she's also, or her company is member of this association. So Paola, you can perhaps say a few words about the association.
Yes, sure. Good afternoon, everyone. Thanks, Antonio, for the introduction. So my name is Paola de Bono, and I manage the laser department at TWI, the Welding Institute. We're based in the UK with headquarters, a few other sites, and we are a member of AILU, and also personally I'm part of the AILU steering committee. So AILU is very pleased to be a collaborator of APIC in occasion of this event. So thanks for this opportunity. And so the Association of Industrial Laser Users, this is what AILU stands for, was founded in 1995, and it is an independent non-profit organization at the service of the laser community. So AILU has about 300 members from 13 countries, which include the laser manufacturers, suppliers of laser equipment and services, job shops, also end user, both from industry and academia. And among the core activities, it is worthwhile including the AILU promotion of member activities through AILU's network, social medias, their magazine, their website, and also AILU is very active in organizing events across a range of laser-related topics, also focus on consultancy services for laser manufacturer. And as I was mentioning earlier, obviously there is an AILU dedicated website and magazine with the intention of raising awareness, supporting acceptance and progression of laser technology. So in essence, AILU is all about connecting, empowering and guiding people who use laser. And you might be already aware, but if you're interested in finding out more about AILU, please check their website. Also, there is a Dave and other members of the AILU's team who will be pleased to assist with any queries.
Thank you very much, Paola. Thank you for all this information. And I also see already Jerome from Phix. I introduced briefly your company, Jerome, but perhaps you can say a few words if you want about Phix.
Yeah, sure. Thanks a lot for the quick introduction. So I'm Jeroen Duijs from Phix. I'm responsible for all the sales and commercial activities. And within Phix, we do the back-end packaging of integrated photonics chips. So either used for like LiDAR applications, but also for quantum sensing for diseases. So the application space that we're serving is very wide, but it's really for all the chips that are coming from the manufacturing and then need to go into an application.
Thank you very much, Jerome. And thank you for your support as well. And as I mentioned, these kind of events are for networking. So in case you want to interact with somebody, what you have the opportunity, of course, after each presentation to make your questions. But in case you want to be connected in the next days with anybody, you can contact us. You have my email and the email of my colleague, Jeremy, that is helping me today with the moderation. So feel free to contact us if you want to be introduced to any of our members or any of the companies participating in this event. And you can see in this slide all the companies registered to this event. So they are, of course, interested in this topic of the mobility for the future. I'm very happy that we are covering all the supply chain. So we have manufacturers of different components, optics, lasers. We also have machine builder companies, manufacturers of LiDAR and head-up displays, companies offering manufacturing services, and of course, users for those technologies. So it's a topic that is very interesting. So I again want to thank our speakers for being today. And yeah, let's go with the agenda. We have 6 fantastic presentations. As I mentioned, we'll have time for question and answers after each presentation. So I encourage you to raise your hands, switch on your camera so you can discuss directly with the speaker. And as my colleague Nerina mentioned, we are leaving a stream on YouTube, so you can also ask questions there and we will bring them to the room. Due to the, let's say, topic today, this quite broad, we have divided the agenda in 2 blocks. The first one is more related with LiDAR and other monitoring applications. The second one is related with laser welding techniques for e-mobility. And we can start with the first one. So Winfried, you are the first speaker. He's head of business of the unit active laser components, and he's going to give us an overview of all the new technologies related with automotive. So the floor is yours, Winfried. You can start sharing your screen.
Yeah, thank you. Okay. Dear Noringa, dear Antonio, thank you for your invitation and organization of another interesting APIC event. A warm welcome to everybody. My name is Winfried Reeb, and I will talk about an overview of LiDAR and other photonics technologies related to applications in the automotive market. Before doing that, I give you a very short overview about Laser Components. So Laser Components is a private-owned company founded in 1982. This is how we celebrate our 40th anniversary this year. As the name suggests, we are focused on components for photonics market, development, production, and distribution. So the headquarters is here in Olching, next to Munich. Here, it is also a production facility for optical coatings, precision optics, fiber optics, photon counters, laser modules, detector modules, and electronics. I think I have all now. Important for LiDAR are pulsed laser diodes we are doing in Canada. And in our new plant in the US, we are doing a lot of different detectors. LiDAR, light detection and ranging, will be an important topic today, in particular, the time of flight operation principle. Here you can see how it works. A pulse laser light illuminates a target, and the reflected pulse gets measured with a sensor. Differences in laser return times and wavelengths can then be used to make a digital 1, 2, or 3 representation of a target. Let's talk about applications outside the car. So some of you will be probably unintentionally familiar with speed guns and speed control. So the portable speed guns can measure up to 1 kilometer, means they can detect you before you can see them. I'm sure you also know the permanently installed speed control in a column on the roadside. The advantage here is that several driving bands can be monitored at the same time. So if you don't like such speed guns, you can install a laser jammer. But this is not legal in all countries, most countries. A laser jammer detects the signal of the speed gun and then tries to disturb the reflected measurement signal. Other application, traffic monitoring, is also a very popular application you can see on motorway, tunnels, or bridges to see what kind of vehicle is just passing by, car, motorcycle, trucks, or whatever. Another application, ACC, Adaptive Cruise Control, is an available cruise control advanced driver assistance system for road vehicles that automatically adjust the vehicle speed to maintain a safe distance from vehicles. If we look into a car, we see that there are many different sensors and technologies. So the cause, unfortunately, there's no perfect sensor that optimally performs all measuring tasks. Cameras, an example, are good for color vision, identifies other road users, lane markers, and traffic signs. Ultrasonic is used for parking assistance and short distance measurements. Radar is used for speed and obstacle detection. And LiDAR has 3D capability and ability to function in unfavorable weather conditions like darkness, a big difference to cameras. Here you can see an overview about available 3D automotive laser scanner technologies. The first automotive 3D scanners are based on years of experience with industrial safety scanner. The scanning LiDAR illuminates a small part of the field of view at a time. The laser is scanned with a rotating mirror across the field of view. As little as a single photodetector, a single pixel or small array captures a return. Solid-state LiDAR is a code name to describe LiDAR which are not using conventional motors, but semiconductor solutions to scan or steer light through a scene. The emitter and the detector are essentially the same, but the rotating mirror gets replaced by a MEMS. Flash LiDAR is different. So it illuminates the entire field of view at once, and the photodetector array captures the return of the entire field of view at once. So flash is mechanically, optical is simple, and potentially cheaper as there is no need for beam steering mechanism, but the requirement for the emitter and detectors are more demanding. Okay, I have to speed up. So other applications. So the head-up display, an example, is an augmented reality display that provides a safe driving environment by showing information derived from vehicle sensor data. Anti-fatigue driving detection system. It's on a matter of traffic safety that preventing drivers from drowsiness. It's a kind of driver monitoring system based on facial 3D imaging recognition and movement detection, such as eye closing. Laser headlight. At the topic of continuous improvement in automotive industry, headlight technologies from halogen, xenon, and LEDs to now doubtless laser is one of their favorite to improve the energy conversion, efficiency, and brightness. Air quality monitoring system. The so-called PM2.5 sensor use laser scattering to radiate suspended particles in the air. Here, maybe the next step could be air purification by using UVC LEDs in the future. Laser indicator or anti-collision brake warning light. An anti-collision brake warning light increase the visibility at the rear end of the vehicle. They warn following drivers not to get too close so that traffic accidents can be avoided. Finally, Rolls-Royce star roof. I have no picture here, so you really have to Google it. Looks fantastic, but well, it's more likely Photonics entertainment in the car. So I will do a very short summary. So Photonics already plays an important role in mobility and will be definitely more in the future. Even if there are some nice to have applications, Photonics is indispensable for safety and healthy reasons. LiDAR sensors are important for safety reasons and in the future for autonomous driving. So if you have any questions offline after this event, please contact me directly. Otherwise, I have to say thank you for your attention. I hope I made it just in time, Antonio.
Yes, perfect, Winfried. I don't know if you can start. Yeah, perfect. You stop sharing the screen. So we have now time for questions. So feel free to raise your hand so I can see you and switch on your camera to make your question to Winfried. You made, Winfried, I have a question because you have made a nice overview of different technologies. Which of them are more realistic today or more real today, and which are still starting in the development process?
Well, most of the applications you have seen, they are already used, like the PM sensor, speed gun, everything. LiDAR is probably one of the hottest topics. And for LiDAR, as I mentioned, the traditional one with the rotating mirror or with the MEMS, that's something which is already in mass production. But of course, all of them you have seen is 905 nanometer. You're probably aware that 905 nanometer is not the perfect wavelength, or it's not A-safe. So there are many developments. They are trying to move these scanning systems to 1550. But it's still 1550 is still very difficult to do, both on the emitter and on the detector side. So the 905 we have, it's something commercial available. It's for reasonable price. That's also the reason the scanner you can find at the moment on the road, all of them are working at 905 together with silicon detectors or cameras.
Perfect. Thank you, Winfried. We also have a question from Shahun from CSAM.
Hello.
Hello, we hear you.
Hello, do you hear me?
Yeah.
Do you hear me? It's clear? Sometimes I have a problem with my microphone. So. Okay, so my question is, so it's like a continuation of your discussion about the wavelengths. So you are saying about the 905, this is kind of a commercially available laser wavelength, so that's why you stay there. But
Yeah, that's.
But and then you said there's a not really available laser at 1.5. Can you make more comment on this? And also, why not a 1 micron laser?
Okay. So in any sensor applications, you have or you need an emitter and a detector. For 1060, it's probably better for going through the air, but then you also need a detector who has a high sensitivity. And this is not really given in 1060. So if you're using a silicon detector, the spectral sensitivity fall down. So 900 nanometer, 850, it's really a peak. So you're getting the highest sensitivity on the detector side as well. And so 905 and silicon is a perfect match. So that's also the reason 1060 is not really used. And the other benefit of 905 is the technology to produce such lasers is very well done. So you get a lot of power from a limited current. So the efficiency is more likely 3 or even more than 3 watts per amp efficiency you are getting. That's something we don't see at other wavelengths like 1060 or 1550. Not with edge emitter.
Thank you.
Thank you very much for the question. Any other question for Winfried? Well, if not, I want to say thank you again, Winfried, for your introduction. Yeah, you gave already your contact, so you are feel more than welcome to contact him in case of any future question. And our next speaker is Raul Bravo from the company Outsight. He's going to talk about some software related with LiDAR. So Raul, nice to see you here, and feel free to share your screen with your presentation. You are muted right now.
Give me 1 second because I need to go out and get back to have the right to share. It is going to take 5 seconds.
Okay, so let's hope that Raul is managing. I can perhaps, while Raul is trying to share, I would like to make another question to Winfried, because you make a nice overview, But we also, you know, that you have a typical Epic question that is, what can Epic do for you? What can you do for Epic?
Yeah.
So what do you expect from in terms of collaborations, and what can you offer?
Really sorry about that. I hope now it's okay.
Yeah, I was making a question to Winfried in the meantime.
Should I answer the question, or?
Yeah, you can answer the question, Winfried.
Well, you know, we are components supplier. So at the end, we have to know from the audience, from the sensor manufacturer, what they have to do for future sensors and what they will need, that the performance of the future sensors will be good. That's the information we need. And then we can develop or optimize the development of our components. On the other hand, we of course can tell you, the sensor manufacturer, okay, these components are available. These are reasonable prices. These are more difficult and more expensive to produce. That's something we can share to the audience. About that, again, we need the feedback of the future sensor development, and then we have to know what products, components we have to develop.
Okay, good. Thank you, Winfried. And Raul, yeah, sorry for waiting. Thank you for waiting.
Yeah, sorry again, new computer, new problems. Okay, so plug and play special intelligence means that it's not only about LiDAR. So we're going to talk about applications of LiDAR, how we can more specifically use this sensor in many different situations. So perhaps just a quick overview of who we are. So we are a startup or a scale-up, as you want, some 80 people working from Paris, France, Sophie Antipolis in Nice, in France also, and in San Francisco. We have won several awards and been working on LiDAR, our team, for many, many years. So now we are focusing on 3D LiDAR, but even at that time was 2D LiDAR that not so many people were talking about at that time. So we are specialists in working with this type of data. And what we are seeing, and the reason we are growing a lot today, is that things have changed in the last, let's say, 2-3 years, a lot in the LiDAR space, in the 3D LiDAR space, because the performance and the cost of current systems have evolved in the right trend at least for customers very, very quickly. So now we have very good 3D LiDAR that are available at the right price for everything except automotive, perhaps. So of course, $1,000 or even less is too expensive for automotive. But what we are saying is that the automotive self-driving car helped, let's say, to start the investment in the technology, but it's everywhere else that the technology is being deployed. So industrial applications, robotics, of course, and a lot of infrastructure based. So this is what's happening today. The problem with all these industries, unlike the self-driving car, is that it's very complex for normal engineers to use LiDAR data. There are many reasons for that. I'm not getting in the detail of each reason, but there's many aspects to the complexity for a normal engineer to use LiDAR. Of course, for example, you cannot really use image processing techniques for LiDAR. It's a very different kind of data. There is no standard. So there are almost 80 different manufacturers of LiDAR, and each one is using their own solution, etc., etc. It's really what is today preventing deployment at scale. It's not the price and performance anymore. So that's what we are doing. What we are doing is helping the market to evolve from an early stage phase where everyone was doing everything to the mainstream situation where there is, of course, hardware, but there is also a specific software that is helping building applications very easily. This is what we are doing, making very easy to make applications from LiDAR. So that means 3 things. First thing is that we are abstracting the complexity of the hardware That means that we are combining different heterogeneous situations and manufacturers and bringing a standard output. The second thing we are doing is processing this data, making the heavy lifting, object detection, tracking, SLAM, volume computation, etc. And the third thing we're doing, which is a consequence of the previous one, is that the narrowband output, it's something you can easily use in any application compared to the raw data, which is massive amounts of 3D data that is hard to process. So I think it's better for you to see more precisely what is a 3D preprocessor with these examples. So in the bottom of the image, you see the raw point cloud. And on the top, you see a full abstraction on that, which is just a dashboard. So a customer that just wants to know how many people are crossing a line, how long are they waiting, etc. For example, in an airport situation. So these are the steps that you need to do, at least, to get to this point. So first, making clustering segmentation of the objects, tracking them, and then providing a higher abstraction level. So if you are asking a customer, going from the bottom, which is the point cloud, and build their top abstracted situation, which is a dashboard, you can see that there are many steps that only some customers are able to and willing to do, whereas the value of the 3D data is obvious more and more for many people. So this is illustration of what we mean. This is raw data, and this is already processed data in real time. So remember, this is done at the same time that the data is acquired at some 20 Hertz, more or less. And this gives you a quick overview of the main features, which are localization and mapping, of course, fusing with GPS data or similar, so you can integrate in other platforms such as Google, perception and object tracking, including static and moving objects. So you can use for different use cases, of course, automotive and self-driving cars, but there are many other use cases like speed law enforcement, city inventory, and many other situations where you would like to have not only a map, but also a dynamic understanding. Very powerful and strong trend we are seeing is smart cities and intelligent intersections, where we are tracking bicycles, pedestrians, vehicles, and detecting events like near misses. That means accidents that have not happened, but almost. Here, tracking people for passport control, for security applications, for many other reasons. Another application which is different is volume measurement in warehouses. In that case, we are fusing the information from many different LiDARs to get a real-time understanding of the volume of stock in the warehouse. That was a static situation. A dynamic situation is that the stock is on a track. So we are making the segmentation of the load against the track itself, because of course you want to measure the load and not the track. So that are good quick overview. Of course, if we are doing that is because we are using the best LiDARs depending on the situation. So we have agreements with more or less 80% of the market, because what happens is that each LiDAR is a good fit depending on the context and the use case. So there is no perfect LiDAR and there is no useless LiDAR neither. There are many niche applications, many different situations where each hardware has more or less advantage and inconvenience. So that's what I wanted to show to you, opening your eyes that the software era of LiDAR is starting, and it is the key enabler, not for LiDAR. No one really cares about LiDAR or 3D. What they want is the value of 3D data. And of course, most of the users are not experts. That's our job. We have been doing that since many, many years, because we are convinced on the value for society to make a safer and smarter world with LiDAR and the right software, of course. Thank you.
So thank you very much, Raul. Thank you for all the explanation. And now we have time for questions. So please feel free to make your questions to Raul. I can start because I was really interested in the application related with intersection monitoring and accident checking and so on. What's the main challenge over there? Is to handle with different vehicle size, the different speeds. What's the main challenge of this kind of application?
Well, there are many challenges. The first is that in many of these situations, you need to merge data from different LiDARs first. So if you want to cover and you're not having shadows, etc., and so that's a first challenge, because you need, of course, to synchronize the LiDARs, you need to calibrate them, etc. And you want this to be done with people that are not engineers or experts, because otherwise you cannot deploy at scale. So that's a first challenge, the challenge of setting up the solution and even deciding which LiDAR you should use at what position, what orientation, etc. This is very real life challenge. It doesn't seem like very technical, but it's a real challenge. Is how I can better use the technology to fulfill my objectives. So that's the first challenge. The second challenge, of course, is what you mentioned, is that you want at the same time be able to detect people, detect cars, vehicles, etc. And you want to be very precise, because you are trying to detect things, as I said, as near misses. Near misses are accidents that didn't happen, but could happen or are almost happened. So you want to detect that so you can correct and take measures so you can improve the situation so there are no accidents happening in the future. So for this, you need to be very precise. So there are several challenges there.
Okay. I see also the hand from Shangon again. I don't know if it's a new question.
Yeah. I have one question about angle resolution. So what I mean, when we try to make a three-dimensional scanning, we have like a attributable angle resolution, for instance, 0.1 degree. Then 0.1 degree resolution means like a 10 centimeter spatial resolution at 100 meter. Is it enough, or you have any required like a spatial resolution at certain?
I'm not sure of having this. Not being able to understand everything. So, are you saying that you have is the question if a 10 degree, not 10 degree? What do you? No, sorry, I'm not hearing you very well. So,
okay. So, for instance, when we scan, for instance, we have an angle resolution. So
yes.
0.1 degree angle resolution. It means at 100 meter position, we move 10 centimeter. So it means every 10 centimeter, we have one data point. So this is kind of a field of view plus like a pixel resolution. And then this 10 centimeter is enough for your like 3D scanning images and then data processing.
I mean, it depends on the application, but typically an object of 20 centimeters is the minimum that you need to able to detect. If you are not able to detect something that makes some 20 centimeters, for example, a cylinder of 20 centimeters diameter, then it's not going to be a very good detection. So in order to answer these kind of questions, what we did is that we built a simulator a LiDAR simulator that helps even our users or customers themselves, even they can do it, to understand what is the best LiDAR they should use or the best combination of LiDAR. It becomes very quickly complex to answer without having data, factual data. So for example, is it better to have two LiDARs with 32 lines closed because they are separated at some time, or is it better to have 164 or 128 lanes, whatever? So we can't answer without looking at the data. So what we did is to develop a simulator that helps to answer these kind of questions. So I would be glad to help to talk outside the meeting if you want.
Okay, thank you.
Thank you, Shahun, and thank you also, Raul, for the nice presentation and the overview. Well, I hope you can be more present in the automotive industry in the future. Yeah, as you can see, our next speaker he was really fast, Dr. Tomonori Nakamura from SCIVAX. Yeah, the floor is yours. Thank you very much for being a speaker today.
Thank you, Antonio-san. Can you hear me? And so can you see my screen? Okay.
Everything good yet?
Okay. I'm Tomonori Nakamura. So as shown in a dotted picture, so from SCIVAX, today I'd like to talk about sensing optics for DMS and LiDAR. Briefly, company interaction. SCIVAX is focusing to maximize science value. Core competence is ultra-fine processing based on nano-imprint lithography. Through nano-imprint lithography, we have three business. The first, nano-imprint lithography foundry. Second, nano-imprint lithography machines. And third, nano-imprinted products. We have many experience for making nano-imprinted optics. That's why, so I would like to emphasize nano-imprint plus advanced optics design lead to the best optics for automotive. We already have two best solutions for DMS and LiDARs. For DMS, we have platanous hybrid diffuser. Hybrid means fusion of diffraction and refraction phenomena. This slide shows this picture shows the FOI of 140 degrees by 110 platanous. Platanous can illuminate very wide region, so that's why I think this optics is matching for in-cabin system. And additionally, the platanous has three strong points: no interference and flexibility for light and low height of packages. For LiDAR, especially flash LiDAR, so we have new optics, Ardisia hybrid dot projection optics. Ardisia can gather the illuminated light into the dot. So that's why the intensity is higher than the diffuser's one. So the Ardisia can illuminate, can get far region information. And Ardisia also has a three strong point. There is no limit of dot power. If we can increase the pixel output power, that we can get much more high intensity dots and flexibility for lights and low BOM cost. So usually, so if we get a dotted light, so usually use DOE system. DOE system usually use a collimator lens, but our Ardisia do not need any collimator lenses. Okay, I will show you the experimental results for DMS and the LiDARs. This is in-cabin rear mirror position DMS results. This point cloud is taken from a Melexis evaluation kit and SCIVAX Platinum module. As you can see, the point cloud very fine and smooth. And in a wide region, driver between driver and passenger seat. Unfortunately, we cannot get the information, the rear seat information. I have one solution. So I will describe later. This is for lidars images. We took 10-meter depth image taken by a Ardisia module and TOF system. Left picture show the IR images, and right pictures is calculated results from IR image in a depth scale. The optical output power in this experiment was only 2 watt. Only 2 watt, but we can get 10-meter images. From the results, the expected range at 10 watt is over 30 meter. Maybe we can use surrounded car sensors, these lenses. Finally, I will inform our future plan. For DMS, we recommend use Ardisia with many dots like this. Actually, the Ardisia dot power is higher than the diffuser's one, namely Platinum's one. Therefore, maybe the dot can get the information from rear seat. For lidars, we can control FOI like this, just narrow one, and the high aspect. So squeezing the FOI, the dot power becomes higher. That's why we can get the far information using high aspect Ardisia. If we attract your interests, we are welcome you because we are friends. Thank you for your attention.
Thank you very much for the presentation, Tomonori. It was really interesting. And thank you also for sharing your future plans regarding the optics for LiDAR. Perhaps you can stop sharing your presentation so we can see the audience, and I can ask now our attendees to make a question directly to you. Jeremy.
Yeah, thank you. Thanks a lot for your presentation. I just have a question regarding your activity. So I wanted to know if you're already working for the automotive industry, and if yes, what is your main challenge to overcome to access to this market today?
Sorry, one more please. So I cannot catch them. So what?
Yeah, sorry. So my first question was, if you are already working for the automotive industry, and if yes, what is your main challenge to overcome to access to this market today?
You mean the photonics market, right?
Automotive market.
Automotive, yeah.
Yeah.
Yeah, actually, firstly, we'd like to focus in cabin system because at this time, we cannot get good. We cannot realize the over 100 meter or 200 meter optics. That's why. So at this time, so we focus on cabin system.
Okay, thank you very much.
Thank you, Jeremy. Any other question for Tomonori? I have a question because I guess your customer will be a LiDAR manufacturer. What would you expect for them, or what can you offer for them in terms of getting a good relationship?
Yeah, yeah. So now, so we are looking for the good partner, and so actually, so flash LiDAR is a at this time very difficult for use to get, because it is difficult to get far information, but so at this phase, so we hope some makers or some car makers, some automotive makers have an interest for me and for us. Yeah.
Okay, thank you. We have another question from Shanghung again, from CSEM.
So thank you. So I have one question about your flash LiDAR. So I guess your flash LiDAR may use SPAD detector, and then I don't know what's the impact of sunlight.
Yeah, actually, so flash LiDAR is resolution is quite low in comparison with usual LiDAR, but so flash LiDAR can get this information many areas. So I think the flash LiDAR has a profit and compared with usual LiDARs. But so I think so we have to improve the resolution by using new technologies. Yeah.
Thank you.
Thank you, and thank you again, Tomonori, for your nice presentation and your future plans in the optics for the LiDAR technology. And it's time for moving to the next block to talk about laser welding applications. So we will start with Christian Dini, is General Manager at Civan Lasers. So Christian, the floor is yours, so feel free to share your screen.
Thank you, Antonio. I hope it works. Are you seeing it?
Yeah, we see it. Thank you.
Great. Okay, so welcome and thank you for joining me today. And thank you for the invitation, Antonio, to present here. I'm going to talk about dynamic beam laser, which means dynamic beam is a laser beam where we can manipulate the beam shape, the beam frequency, and a lot of beam characteristics. So I'm going to talk you through a short presentation here, but let me start quickly with an introduction about the company. Civan Laser is an Israeli company founded in 2008. And basically for the first 10 years, it was a tech company developing the technology originating from telecom into industrial laser use in the sense of materials processing. And in 2018, the first 14 kilowatt laser was delivered. And last year, our first 100 kilowatt laser was delivered. That's just a side note. That's not necessarily the product range we're talking today, but just to show the envelope of the company. So all technologies are vertically integrated and available in-house in Jerusalem. Also, we are also using high quality brand components. So what are we bringing to the table? I already mentioned we can change, for instance, the video. We can change the beam shape, and not only to, let's say, given shapes, we can create literally any shape. We can change the frequency of that shape. And as this is working with megahertz speed, we can actually create a sequence. So what that means is, instead of having one beam shape working being the best compromise you can find. We can have several beam shapes working, being the best solution for each individual issue that you might find in your welding application. I will point out a few welding application issues on the way. Finally, we have also the ability to focus steering. For instance, in the scanning application, we do not rely on a f-theta lens. We can do that, but what you will typically known as a 3-axis scanner, but we do it electro-optically. So no moving parts, no wear, no tear. That's basically the idea of Civan laser, what we are bringing new to the market that's not existing anywhere else in this configuration. And one of the beauties is all this freedom, these degrees of freedom you have, you do them digitally. You don't touch your beam delivery system, you don't touch your laser. All you do is you create your beam shape, power distribution, whatever strategy, you do it on a screen and you upload it to your laser and you're basically done. And that gives you the ability to create a lot of different beam shapes. And as you can see here, for instance, they don't have to be static. There can be an overlay of motion. These beam shapes can be rotational symmetric, but they can be asymmetric. And you can, for instance, steer them around. If you have curvatures, if you go around corners, then you can move them always around in order to meet the right direction of motion, the trajectory. So that's basically the freedom in terms of shapes. I already mentioned, oh, sorry, I'm too fast. That's for instance an example. Since we're talking electromobility, I used the similar materials here. You have aluminum and copper. And you see this is a traditional single mode laser beam. And here you have a different beam shape. And it really pays off in terms of hot cracking, for instance. So you can eliminate the problems you will encounter, for instance, with hot cracking. Problems I mentioned before are typically humping. That means if you go fast, then your topography of the welding seam is getting unstable and you get humps. You can have cracks, and the last one is porosity. And all that is basically driven by instabilities of the keyhole and the melt pool. And that's basically what we are all about. We are basically providing new means to manipulate the melt pool in terms of gradients, in terms of flow, and that's basically done mainly by controlling the keyhole. You can put a shape to the keyhole. You need to keep it open, and then you basically have the shape we already discussed. And the other factor that's a huge leverage on terms of welding quality is the frequency of that shape. So here you see an example of same material, everything else is the same except the frequency that was used for this beam shape. And so you can see you have a very unstable situation here. You find porosity. You can actually see here this is basically like an eruption of molten material. You go higher to the frequency, you already see it stabilizing more. This is still not a wanted topography of the welding surface, but nevertheless, the weld here inside is already quite nice. But here, in the end, you can achieve something that is acceptable from the top of the weld, but also you have no pores, no cracks. So that's basically the goal of any weld seam. And so we have the shape and we have the frequency, both very relevant parameters that you can manipulate. And since, again, we're doing this at megahertz, we can create a series of different beam shapes addressing each individual problem. Because porosity typically is something you want to steer the melt pool. to keep the keyhole open. Humping is a periodic syndrome, so you want to disturb the periodicity of it. And hot cracking is typically an issue of thermal gradients. So you would use a flat thermal profile across the weld section in order to avoid cracks. And switching with megahertz, we are able to basically apply all strategies at once. Just an example, if you weld with 30 meters per minute or 500 millimeters per second, then you have about 1 millisecond at a particular place at the weld. So within this 1 millisecond, we can apply several beam shapes and address all the issues. And we do that without moving parts, because if we would come to moving parts, then the frequencies that typically applied today for moving the beam is low kilohertz range. So we compare low kilohertz range of moving an entire beam to megahertz range and moving energy distribution inside the beam. But since we mentioned this as opportunities in e-mobility, so, well, it starts with the blank sheet of metal. If you have applications like coated steel, for instance, tailored blanks for hot formed parts, you can weld them directly without grinding down the aluminum silicone coating. Obviously, this is not the result you want, but if we would make, typically what you want is the opposite. You want to have a totally homogeneous mixture, but then you won't see anything. So this is our proof that we have control over the weld. Next one is copper. This, for instance, is an example of 2 times 3 millimeter copper. Copper welding is obviously hairpins, bus bars, but also power electronics. And there, for instance, you really rely on not having sputter. If you have sputter in your power electronics, that's obviously the last you want with having loose little copper particles flying around in a high power electronics. So controlling the melt pull is the key to have no spatter. Another application, also this is aluminum wheels here. This is a steel part, but that's a project we made with a steel rim company. And because of the beam size, the beam caustic, this is single mode laser beam. We have a very long Rayleigh range, and so we were able to apply the beam directly vertical here. So this is 2 parts fitted together. And what you typically would do is you would go from an angle in order to not hit one of these 2 sides. And what it will give you is a short weld seam here. So with this caustic and the way to manipulate the beam, we were able to do it directly parallel to the left part, following the connecting surfaces of the 2 parts, and provided a much deeper weld and a much stronger weld too. Next one, which is I think one of the highlights, is the welding of die-cast aluminum. Die-cast aluminum is a material that's really everywhere. But for an example, heat exchangers or the housings of power electronics of the inverters are made from die-cast aluminum. So the problem is they get sealed when everybody's built in, and then you want them to be gas and water and liquid sealed. And the problem really is the H2 that's trapped in the material itself. So typically you get a lot of porosity. So some strategies is to weld it, but weld it twice. First time, basically get the parts together. Second time, remove the trapped hydrogen. But that second round is time consuming and leading to the, let's say, it's prone to hot crack again. So with our control over the melt pool, we can achieve a very high rate of outgassing, allowing the trapped hydrogen basically really to get out of the material and only leave this. So the key, the benchmark is porosity below 3% of the surface. And that's something it's very, very difficult to achieve today with regular lasers. So we have a real edge with our technology here. Another one is battery cooler. The typical application, welding application in automotive so far was a few millimeters to a few centimeters welding length. But with these days, with the batteries getting larger and larger, basically the whole bottom of the car being a battery, the cooler has the same size. And with the cooling channels on it, you have several meters of welding paths you need to apply if you want to weld this. Welding would be better than brazing because it's less energy consuming, and you have basically a clean material in the end. You don't have I'm lacking the word in English, but you can reuse the parts. Sorry for that. I can't remember. Recycling. Sorry. Yeah. So it was and it's an issue of recycling, because with the brazing, with the flux, you don't have a clean material anymore. But in order to do that, you have to weld very fast, and that's where you get to 30 meters per minute, for instance, and that is where humping comes in. And so this is basically a technology that can move the speed barrier of high-speed aluminum welding by quite far. Right now, it's actually by a factor of 2 if we look to other solutions on the market. Sorry, this way we have this similar materials when you think about welding bus bars to batteries. And so what you don't want is don't want to have intermetallic mixing, because that is again prone to cracks, and we all want these joints to basically last long, because if this is the battery and the bus bar, then obviously this is basically the performance or the durability of your car. So that's another thing where you have a much better leverage on the design of the quality of the weld joint when you manipulate the beam, when you control the beam in the way as we do. So that's basically what I wanted to rush you through. Sorry for the speed. Key takeaway is the dynamic beam laser enables you to control the melt pool, the keyhole, so that you have the thermal gradients, the flow dynamics. That's something you have a direct control mechanism here. And that enables us to weld at higher speeds. We can weld crack sensitive materials, something like 6000 series aluminum, for instance. We achieve deeper penetration welding on air, so in atmosphere. The dissimilar coated materials, you have a parameter you can basically influence directly the mixing or not mixing of the two dissimilar materials. And finally, the die-cast aluminum, which is something that's today, at best, with a lot of compromise is weldable. But with the control of the outgassing, this is a big improvement as well. And with that, thank you for your attention. And by the way, if you happen to be at Euroblech, then please stop by, come and see us, and then we can talk a little bit less rushed. So,
thank you very much,
Antonio.
Christian. Yeah, thank you very much, Christian, for the overview of your technology and a lot of applications related with the immobility. So it's time for questions. So feel free to raise your hands. I have two questions. One is related with the wavelengths you use with these technologies, or you try with these technologies?
It's 1064. It's infrared. So
Have you worked with any visible wavelength up to now?
We did, but so far that's basically, let's say, mind games. So for now, there's with the ability to control the focal spot in a way like that, the power in the 1064 is, let's say, much cheaper, so you get a lot more power, and then you have it's a commercial trade-off, whether you go green or you go red. But going green typically means you're dealing with frequency doubling crystals. That is also not necessarily the most easy task. So for an industrial system, straightforward industrial system, we believe the 1064 is a very good wavelength here. Particularly as we see, the 6mm copper, for instance, we welded that with 2.5 kilowatts. So it's you can go very, very fast. So this is completely unseen welding speeds in copper.
And my second question is related with the moving or the dynamic beam shaping. I was curious about if there is any kind of energy losses to detect, or all the power of the laser is transferred to the final beam, even if you are moving.
Well, the principle of operation is coherent beam combining and optical phase array. So that means we have interference. We have constructive and destructive interference. There is obviously some loss, but that's basically taken care of inside the optical head. So whatever we quote, you get it basically out of your laser. So, but yeah, we have some. We have a water-cooled optical head because there is some loss.
I can imagine. Okay, we have a question from Carr's welding field. Carr, please.
Oh yeah, Christian, thanks for your very interesting presentation. Yes, I listened to a similar one the other day at the AILU conference, and wasn't enough time for a question. But I wanted to know, because I still haven't seen one of your lasers yet. Do you have many installations in the UK?
Actually, not in the UK, no. I would need to invite you to mainland Europe to come and see. But maybe this can change now. So we are looking forward to have some cooperation in the UK as well.
Yes, it's a big decision to make, especially for companies of our size, and because of, well, it's a big decision because it's a big capital piece of equipment. And so you're making all the right noises.
Thank you.
I wish you well with it. I mean, I'm very interested to hear about what you're doing with copper, because copper seems to be the sort of the material of the moment, and we're doing a lot of copper ourselves, but we're just using the IPG with the wobble feature on it, and that seems to work really well. Yeah. So I haven't done any pulse shaping yet with what we've got. Maybe that's the next chapter, because often there's a new chapter. But no, I'd like to see a machine working, and I'd quite like to have a bit more of a discussion, not today or tomorrow, but
well,
to Germany. But
well, I would really like to invite you to we are just starting a facility in Hanover, so where we will set up an applications lab as well. You're always welcome to come and see us in Israel, but other than that, if you prefer Germany, then there's a couple of institutes running lasers already, so you can see them in operation. Or
running them, are they?
Sorry?
The Fraunhofer running them?
Yes. Yeah, there's IFSW, for instance, IWS,
with what?
And then also the FAU in Erlangen. So there's a few lasers now around, and as I say, soon up in the north as well.
Yeah, great. Well, good luck with that, and we'll have a proper catch up. I think I've got your email, so
yeah, let's stay in touch. Great, thank you. That's what this meeting is about.
Yeah, no.
That's right. That's right. So nice to see this kind of interaction. Christian, we have also a question coming from YouTube. It's from Julien Gatto from EPIA. He's asking if it would be possible to create several foci at the same depths, at different depths, sorry, maybe you sort of approaches the problematic using the angle beam.
So did I understand right? This is basically several beam profiles at the different focal lengths. Correct. At the same time or nearly the same time. We can move the beam in the z-axis in, again, megahertz speed. So basically, we can move very fast, but we don't. It's not possible to have several spots at a different focal lengths at the very same time. But as I say, for the material response time, typically this is much slower. So we for the material it would feel like the same time.
Okay, I think he's not meaning at the same moment, let's say.
Yeah.
That could be quite difficult. So I understand that dynamically moving the depth.
Yeah, yeah, we did deep penetration welding, and we did of several tens of millimeters. I mean, 50-ish, 50 plus-ish, and we did also cutting, for instance, where we used that. It really shows an effect, yeah.
Okay, thank you. So I think we answered the question from Julien. And thank you again, Christian, for a great presentation and showing us your technology. And
thank you.
We will move to the next speaker.
Okay.
We also heard Paola, so hello again. She's a section manager at TWI, and yeah, she will present us also their projects related with laser welding. So Paola, the floor is yours.
Thank you very much, Antonio, for the nice introduction. So let's see, should be able to share my screen now. Hopefully you're able to see.
We see your presentation, and probably is moving to full screen. Yeah, we have it.
Fantastic. Well, I'm very pleased to be here today. Very interesting presentation so far. In the slides that I will go through, in the talk I will go through, basically, I will just cover some joining challenges that are being faced within the rectification. So some example, and where obviously laser technology is involved and can help. So just a quick snapshot on the content, some background about TWI, and then moving to the main topic of the presentation, and then some summary and conclusion. So regarding TWI, we are a research technology organization with the multidisciplinary expertise in engineering, materials, and joining technologies. Our headquarters is in Cambridge, and just specifically looking at the laser division, we've been involved in laser processing since the 1960s. So since laser technology started really taking up within industry. So in terms of core areas we cover, obviously there is the laser joining side, autogenous welding, hybrid, laser brazing, but also laser cutting, looking at high precision cutting, but with a big focus on decommissioning application for nuclear and oil and gas industry. Then a laser surface engineering, that looking at laser cleaning, micromachining, laser hardening. So maybe for another talk about some of the laser surface engineering application also might be a good fit for to address some EV challenges, and then also additive manufacture, powder and wire based technology. We focus obviously on metallic material, but also on ceramic, polymeric material, dissimilar metals, dissimilar joining in general. So going to the topic of this talk, obviously here there are the three main types of battery cells that are typically used for battery modules, battery packs, and TWI has been involved in several activities looking at these three different types of cells. But if we look at joining challenges, definitely there is the production side of things of battery packs. So how a good quality weld is achieved across the full battery module, battery pack, and also in terms of electrical performance, how you can achieve a high localized heat input. And also there is often a need for dissimilar material joining. Looking at another challenge, certainly the thermal cooling is another aspect that needs to be taken into account to prevent any thermal runaway or battery packs catching fire. So looking at how to address those challenges, and obviously the weight aspect. So how you could design the battery pack, which material to involve, which technology can be involved in order to reduce weight. Obviously, we talk a lot about electrification for automotive, but we should always remember it's not just limited to automotive. There is a big focus also for aerospace application and also much wider application across various industry sectors. So then moving to lasers, so why it is suitable, why it is attractive to address some of the EV joining challenges. So definitely is a very flexible process, non-contact, highly suitable for volume production, but also capable of covering a range of materials and thicknesses that are typically considered within EV application. Also the flexibility on processing a range of materials, also being capable of coping with some of the challenges that, for example, reflective metals like copper and aluminum typically require, and also the high localized beam, the possibility to reach very small beam spot size, and also the scanning technique that have helped to control intermetallic phases, brittle intermetallics, for example, in these similar joints. So a lot of aspects that lead to consider a laser for this application. Some here, these slides capture just some two main types of joints that are typically encountered in battery modules, battery packs. So certainly there is the busbar to terminal joints, depending on the type of cell, cylindrical, prismatic, pouch cell. Obviously the thicknesses, the material involved slightly change, offer different types of challenges, and there are several approaches that can be taken into account. Obviously there are the concentrated infrared beam using scanning approaches, so with the use of a wobble head scanner technology. Also short pulse laser technology has been considered, for example, for a material combination that lead to intermetallics, so a different approach to the one that perhaps a fiber laser technology can cover, using high frequency short pulse interlocking mechanism. And then there are the more conduction modes beam, so the emerging blue laser technology. Obviously we come across the green laser. Also Christian earlier was talking this interesting presentation about dynamic beam laser. There are obviously the ring mode laser beam. So there is a range of options available trying to address some of the joining challenges for EV application. And also we shouldn't forget about the battery cases. Typical material are aluminum, steel, different joint configuration, thickness ranges that vary from 1 to 5 millimeters, and in this case partially penetrated joint need to be achieved, and the use of a wobbling technique have helped, for example, to overcome some porosity challenges that typically are encountered for this type of a joint. So what else to consider for laser when joining for EV application? So definitely the temperature. So there is chemistry within those battery cells. So typically it's important to control the heat input, avoiding to go beyond the temperature threshold of those battery cells. The chemistry inside those battery cells, the fixture design is very important. So making sure there is a uniform contact across the full battery modules. So so validating those fixtures during the scale up phase. And in this context, also when developing parameters, let's say at coupon level, offline simulation has proved to be very helpful. So you can upload the design of the module, the design of the fixture, the laser cell, and you can identify at a very early stage if there are any constraints in the weld path in terms of access of the beam. So TW has been working in these many different areas, and we've been supporting industry to solve some of the challenges also during the scale-up stage. Very briefly, we shouldn't forget about in-process monitoring. It's a very hot topic in general, not just for electrification, but has proved to be very important to actually helping to develop a robust process. So there are keyhole depths monitoring devices like the Precitec IDM you might have come across, so the LDD from IPG, just as example, able to measure the keyhole depths in line, in process. And also TWI has been investigating some image monitoring technique looking at the stability of the keyhole, and this is very helpful also to reduce some post-welding inspection that maybe add time into the operation stages. And then in terms of some case studies, I'm just aware of the time. So basically, TW has been involved in several collaborations. So this is the case of a government funded program collaborating together with BMW, where we've been involved in the different stages, from the very early stages of tooling design manufacture, obviously contributing with our joining expertise applied to this challenging application, and then obviously the scale up and the assembly, and also the handling of high voltage cells that is not trivial. And here there are some links. I believe these slides will be shared later on if you would like to find out more, and happy to take questions also later on. And this is also another example of ongoing project, in this case funded by the European Commission, and looking at the development of a smart battery technology with lightweight design. The project is called Albatross, where again TWI contributes with its welding expertise, so joint process development, validation, and scale up to demonstrate the technology at the battery module battery pack stage. So just to conclude, definitely electrification, there are many different challenges to actually achieve a sound joint And there are different factors contributing to achieve those sound joints, also depending on the type of cells, battery cells involved. And it's not obviously just about, there are several laser approaches that can help, but also considering the aspect of tooling and robust scale up. So go through all the different steps during the scale up is extremely important, and TWI will be happy to support this industry and keep contributing. So thank you very much for your time. Happy to take any question.
Thank you very much, Paola. Really interesting to hear about all the projects you are managing there. And yeah, as she mentioned, it's time for questions. I have one question. It's related with the short pulses procedure you mentioned. Do you think it's going to be feasible in the future, or is going to be still reduced to some particular application or niche applications?
Yes, so obviously the technology is quite interesting because it introduces a different mechanism of joining those, don't know, for example, aluminum to steel is a combination that is attracting more and more interest. Introduce aluminum instead of copper, for example, to decrease the weight. And I'm aware that, for example, Trump UK is working on a higher power system to actually overcome some of the throughput aspect for example, to actually meet the volume production target. But definitely, yeah, we've been working also with Trump UK, and there are some interesting results there, and there is some good promise.
Good, thank you. Phil.
Yeah, nice to see you, Paola. Long time no see.
Thank you.
It's been pre-COVID, I think, since I last saw you. But just wanted to go back on one of the slides you showed. You showed some copper that looked like it was welded straight onto a cell. I'm going, oh, really? Have you really done that? Have you done a copper to aluminium weld straight onto a cell?
Well, obviously for cylindrical, I believe that's the style. So that was more a copper, yeah, to steel, and yeah, copper to steel, where you can, and then the challenge is how you keep that partial penetration weld. So it's not trivial, but I mean, it is achievable.
It's achievable.
Yeah, obviously on the negative terminal is the one maybe more sensitive to the fluctuation. I mean, in terms of the positive terminal, at least for cylindrical, there is still a gap underneath, and you can sort of it's more accommodating. But I mean, we've been working with clients developing laser procedure for cylindrical cells.
So you can't tell me who your clients are, but because none of us can. But what we find when we're trying to weld through copper is that we end up, once we've opened the weld pool up, it just keeps flying through the copper, and then it will go through into the steel and then not stop. And so often it's difficult to maintain the temperature restrictions on the cell. And so I was surprised to see you welding straight onto the cell. I think if you can do it, maybe I might be able to do it as well. So.
Yeah, I mean, single mode laser technology, the small beam spot size that now are achievable, for example, wobbling technique, that they have been helping. But yeah, it's not.
Another time for discussion over coffee.
Absolutely.
Thank you so much.
So thank you, Phil, and thank you, Paola, for nice. Francesco, do you have you hear your hand?
Yeah, can you hear me?
Yeah, thank you, Francesco.
Thank you very much, Paola, for your presentation. Just in your introduction, you mentioned that TWI worked also with plastic. Okay, and I'm interested in generation of materials, new materials within plastics, in nanocomposite, and in particular nanocomposite. Did you work with that kind of topics, or TWI plan to work on that type of topic?
Yes, so for example, we try to look also at some innovation aspect, obviously, for example, how to combine composite to metal as well. So we've been, it's not obviously.
This is not a question of welding, by the way. I don't know if I'm out of the topic.
Yes, so I would think it would be the case of understanding what's the matrix material. If you're looking at carbon fiber versus glass fiber, so we would need to understand a bit more the details. But we have
nanoparticles within polymer. That's the topic.
Nanoparticles. Okay. Yeah. So perhaps we can have a discussion on this topic. But so we have a system that looks at the lasers technology with some embedded temperature monitoring, real-time temperature monitoring, so you can develop the process. Also, I understand that the process window with this inline monitoring sensor. So perhaps, I guess, yeah, the nanoparticle, the carbon nanoparticle, might absorb some of the laser radiation, so we need to understand that the design aspect related to that. But certainly we have expertise in-house, and we're happy to discuss further, Francesco.
Okay, thank you. Thank you.
There should be my contact in the presentation.
Yeah, I pick up.
And yeah, so please feel free to contact me, and we can.
Okay, we can discuss more on that topic. Okay, thank you.
No worries.
Thank you, Francesco. And well, again, if there is any people interested in contacting somebody, also let us know if you want.
Okay.
If you don't reach,
okay,
if you
Antonio,
don't reach any contact.
I don't want to.
No. You can contact Paola directly, just in case somebody didn't pick the right contact. So just a refresh. So thank you again, Paola, for a nice presentation. And we go with the last one, Phil, Director of Carr's Welding. So the floor is yours. You're muted now, Phil.
So yeah, no, I've just put the screen up. I'm a bit clunky on these sort of things, so excuse me. Always say it's a young person's game these days, but no, we've been around. You see my screen all right, Antonio?
Not yet.
Okay. Why not? Still not?
No, we only see your camera.
Oh yeah, there's one more button. Okay.
Now we see it.
Okay. You got me?
It's perfect, Phil. Thank you.
Great. Yeah. Okay. So we're sort of like the workshop. We're a job shop, Carr's Welding. We're only 12 people. We're a small SME in Northamptonshire in England, and not big, but small, but perfectly formed, I was thinking. And we've been around, not as long as the TWI, but we know everybody. We know the TWI and everybody down at NTC, and everybody sort of gets on as a happy family around here. So laser welding is what we do. Laser welding is about the only thing we do. But as far as e-mobility is concerned and electric cars, it's all about batteries for us. And so I just want to tell you roughly a little bit about the company, a little about where we think the market is at the moment. So we're very much into the copper and aluminium interconnections. We've got 6 current projects running on battery applications at various stages. Some are just making modules for, some we're still prototyping, some we're still developing the technique to get the procedure right. A lot of it tends to be migrating towards the oscillating welding head we have on the IPG, but not everything. And so we're mainly welding prismatic cells as one pouch cell application. And so really, when it comes to e-mobility, it's all about interconnecting batteries, lithium ion and lithium titrate. And where we are at the moment, where we are with how we're doing that and what we're doing with welding, but also where we're sort of moving forward to where we think we're going to be in a few years' time. And the last thing I want to tell you about, a little bit about Sunny Laser project, which is something that we won with the help of TWI, and we're currently running that as a small Innovate project, and that's going okay. So just briefly, company here, so Carr's, we've been around. We've been around since the early 90s, and we didn't really get into laser welding until the late 90s, and then just this amazing tool. I mean, it's just, yes, it's so precise, and I could go through a big slide about why we use laser welding, but it just works. And it seems to break a lot of the rules that we did with conventional welding. I came up the road of using conventional welding and making conventional welding machines or dedicated systems for big companies. And all the sort of rules about dissimilar metals, about the amount of carbon you can use or you shouldn't use, or you should use, and what gas to use. It just staggers me that the laser, as we've started to hear about new technology again for pulse shaping. So we haven't got pulse shaping, we've just got continuous wave. And if I just put on a little, I'll just put on, I don't know if you can see my pointer here. There's the two different types of laser we run at Carr's. We have the pulsed YAGs and there's the continuous YAGs. Mainly Trump's, but we've just bought an IPG, which is the fiber laser. And because you see, recently we've been running a couple of Innovate projects. We've been introducing a bit of ultrasound, and now we've got the oscillating laser beam, and that's brilliant. Not just for aluminium, but all the sort of non-ferrous materials. It's really good. So today I really want to focus on copper welding, only because I can see that's where most of the batteries we've done in the past have all been aluminium to aluminium connections, interconnects. We've done lost track of how many projects we've done now, but it seems to be going copper. So I just want to talk a little bit about what you can't do with copper. Clearly, copper is really, really great conductor. Unfortunately, because it's a really good conductor of electricity, it's also a really good conductor of heat. So it makes it quite hard to weld because it just basically sucks the heat away. So if you look at this this weld down here at the bottom here, I don't know if you can see. I wonder if I can put on a different pointer. So I'm looking at this weld here. This weld is basically a connection through onto a cell. It's like copper isn't great because it sucks away the heat. It can actually produce porosity, and of course the slightest amount of corrosion, contamination would produce a pore, and that's obviously what you can get in a weld here. It's a shame really, because when you're welding cells, you really want to make sure it goes first time. It's hard to cut it off and start again with a new one on. But here we have the pulse JAGs as well. So if we do get one that we get welded and we have to repair, then we can repair. And also bring your attention to this weld over here. There's three spots we've done all with the same conditions. Actually, it's the same as this run of welds here across the middle here. Doesn't look too bad as a string of welds on copper, but when you do them as separate, you realise how hard it is, just dropping a pebble into water. It ripples like mad, and it freezes very quickly, and consequently leaves a sort of a tricky sort of surface on the surface of the weld. So generally speaking, you very easily get blowholes. You can very easily get sort of surface roughness. But generally speaking, once you get the weld pool open on copper, it's quite good for getting a good consistent weld. typically with the IPG and the wobble welding. I say that because we've done quite a few couple bus bar systems in the past with pulse jags, and when you're only using a very high pulsed energy, pulsed for connection copper, you do get a very variable result, and so I don't recommend that. It's possible, but it's something we steer away from now. And there's a few points there about what I would avoid when you are welding copper. So generally, the limitations of copper, it's all about, you know, getting that weld established, and can you get absorption into the energy, so when we get through into where we want to make sure we get a controlled weld all the time. And Paola will, I'm sure, will confirm with me that it's not the easiest of materials to work with, and but getting the weld port open and getting it warm and getting it then running around, it is consistent. So we do recommend it. We are doing it on some sort of pre-production packs at the moment, and interconnecting bus bar systems. And I just want to show you a few examples here. So now this is our special machine. I'll talk about that. First. So that's me in the middle there, looking glum in the middle. Right? Don't know why I'm the only one not smiling, but it should be. This machine has really opened our eyes to what you can do on non-ferrous materials. I mean, it's just a beautifully precise and repeatable machine. The wobble welding, as they call it, we like to call it sort of scanning, or it's like it's a scanning weld beam across the width of the weld, and you can have various little different shapes, but generally speaking, we use pretty much a circular shape in most things, sometimes a linear straight. This basically allows you to control the depth of the weld and the shape of the weld, and it's really nice in non-ferrous materials. Basically, it's just more controllability and repeatability when it comes to the welds. And with some welds, you want to do a sort of a preheat, post-heat, and you want a bit of some dissimilar metals. And so you can do that with an oscillating beam. So the oscillating beam is of hundreds of hertz, and it really does give you a nice looking weld as well as a consistent high quality, and brilliant on copper. Paola talked about it. You want a really high small spot, single mode if you can get it. We've got a multi-mode, but we've only got the 100 micron fiber here on our system, but it does beautiful welds up to 4 or 5 millimeters deep into copper. Really nice, consistent, low impedance. And so we're working on a few projects on research, and can I just talk about a few applications first? So this is very typical of the sort of thing you'd see in my shop today. Just as on the copper, on this circular, there's this weld here. As you can see, the weld gets bigger as we come around, as with the preheat from the weld where it started to put a bit of heat into the job, so that it looks a little bit bigger at the end. So this is the end of the weld. We start here. Now that is actually 10 mil across here, so it's only quite small. And it is copper, although it doesn't look like it is. It runs into copper. And that is the cross section. You know, the two bits of material, 2 mil thick bus bar system that we're making here. That gets too hot to be a cell weld, but it's really good connection for a bus bar anti-connecting system. These other applications, can I just talk about briefly, are little modules. This top one here is cylindrical cells welded together with aluminium bus bars. That's quite a small module. They use quite a few modules to try and manage the heat. Quite a lot of motorsport applications, they really use the power and the energy, and then they dump it all back in and they get very hot. So they have to try and they manage it by keeping the modules quite small and sucking the heat out and trying to keep the energy right. They don't last very long. And so this other module we got down here isn't motorsport. This is more like a sort of high performance car. Pretty old tech now. Cylindrical cells all sort of fused into a big water cooling jacket, and then we weld these big bus bars on the top. Bit clunky, but it worked, and we're still driving around the roads now, and we're very proud to have finished that project. And I can't remember exactly how many there are, but I think there's over 300 cars on the road, probably people's garages. That gives you a bit of an idea of what we do on a day-to-day basis. I don't know how much time have I got on. A bit more time to talk about my research project. Have we got time, Antonio?
We have time.
1 minute? Because what I'd quite like to do is just switch my screen over to, if I can just go on to this other slide. I just want to look at this slide here. I don't know whether you want to see it full screen mode. Sonic Laser, we were very lucky to win an Innovate project with the help of TWI. And what we're doing with this project is we're introducing ultrasound into the bit of metal that we're actually welding.
Phil, but we are still in the previous presentation.
You know,
see your new slide.
Let's just get back to that. We got that?
Yeah.
Yeah, cool. So this is a setup for what we've been doing. We're welding aluminium. It's all the grades of aluminium that we've been welding with the batteries. So 3003, 1050, but also we're using some C100 and one for the copper connection. But basically what we're doing with this project, we're not even halfway into it now, but we have got some very interesting results. I can just give you a little snapshot. We've been introducing ultrasound into the material that we're welding. This little scheme down here shows we're welding a butt weld. But most of what we're doing now, we've moved on to doing lap welds onto battery connections. So we're actually only introducing these ultrasound on the top plate. And but so suffice to say, I just wanted to introduce the idea that we're on research, and we will be reporting in March at ILAS next year some of the results. We've had some very encouraging results already. Basically what it's doing is, as we introduce the ultrasound, it refines the grain structure. And the grain structure is important, because that's what you end up with. We end up with a weld, a solidified weld, but the grain structure of the weld dictates a few things, like how the intermetallics are formed and how they are distributed across the weld, and also the grain structure itself of that weld. And we're finding that we can actually get much better, well, we can get a faster speed and we can get a stronger weld. But at the moment, we're just trying to get some really good baseline weld information on the aluminium and the copper side. And but I'll have more information to report back next year about this. Suffice to say, I'm quite interested because it's opening the window into slightly new areas for us. But it's all related to battery welds. And so we're at the stage now where we can weld the terminal onto the battery, but we're trying to make sure the ultrasound doesn't go into the cell itself. So this was early stages, but I just wanted to introduce you to the idea of Sonic Laser. And so basically that's cars. I'll just put up the other screen so I can come out there. Can I just say thank you very much for the opportunity to do this presentation today. We've, always happy to do a little bit, tell you what we're doing. And, you can tell I'm clunky at this.
Thank you very much. Thank you very much, Phil.
And if there's any questions, more than happily try to answer them.
Thank you. Thank you for nice presentation. So as Phil mentioned, time for questions, if you have any. You mentioned some challenges about welding copper. what was the let's say in terms of lasers? Do you miss something in terms of the characteristic of the laser? You think that other powers of different kind of pull shapes will help, or is a thing related only with the material that is not easy to solve with the technical development of new sources?
Yeah, well, we have the oscillating beam, and we have obviously the issues about copper getting really hot, and so if you're not careful, it gets the component you're welding to can get too hot. We have a job at the moment which has got like a plastic insulation on it, and it's not a cell, but it is actually an insulating part that it mustn't get too hot. So we've got a temperature of 120, I think we can get to, and we are keeping within those terms. But as the copper gets bigger, thicker to carry more power, and the batteries we're working on are getting more and more powerful, I can see it becoming very interesting to see how we try and keep the heat, the overall heat down. So I think the moment with laser welding with with the multi-mode 1060 nanometers does work, and yes, we can clearly get a good result. But I'm listening to a lot of new stuff that's coming along. But unfortunately, when you've invested into new equipment, you then have to make, for small companies, we have to use that technology and move on. So, but we'll be looking with interest to see if pulse shaping really is all it lives up to be. We'll continue welding copper with the oscillating beam as it works really well, and of course aluminium as well. But we'll see. So I'm yet to be convinced about the pulse shaping. Yeah.
Okay. I have another question about the project with the ultrasounds. Okay. I guess you have preliminary results, but how do ultrasounds affect the battery itself? Is there any movement in the components inside the battery, or the battery remains stable and it only affecting the welding process?
Yeah, no, I totally understand that. It's one of the risks we've got in the project. And the trick of doing just vibrating, exciting the actual bus bar that we're welding on the top means we don't actually send any of the ultrasound into the cell. Inevitably, as we weld it onto the cell, then there will be some transferred into the top part of the cell. Now, we haven't had any feedback yet to any detriment to the cell, but we do know that there are often connections in the cell that have been done but use ultrasonic welding, which can be fatigued by the ultrasound that we're using. I might say that I don't see, but this cell here we weld in about 3 or 4 seconds. So it's not a huge amount of ultrasound that actually go into the cell. But we've yet to, part of the project we'll be looking at the detriment to the cell. So we yet probably tell you in March if that's okay, when we've done that project.
Okay, I will keep it in mind because I'm interested in this kind of combination of technologies.
Yeah, no, ILAS, March 21, I think it's a good time for the diary for next year.
Okay, perfect.
Thank you.
So I don't know if there is any question for Phil. I think if not, we can close the event for today. I'm going to share my screen for a final slide with a summary. Let's see if I find it. I don't find it. Just one second, please. Oh, here it is. Sorry for the delay. So just as a summary of the things we discussed today, well, we have a presentation in 2 blocks, as we mentioned at the beginning. Regarding LiDAR and monitoring, we saw that photonics is more and more present in this automotive market. So we heard about LiDAR, about safety and heard automated driving, monitoring of different parameters, even environmental parameters. We have a nice presentation about how to bring the software to mainstream applications to solve the challenge of handle on one side the input of different sources, and also to have a solution useful for non-experts in data processing. And I was interested in applications like intersection monitoring and vehicle tracking, for example. And the last presentation of this blog, we heard how non-imprinting process can be a solution for sensing optics. So we saw some solutions for dot projectors, and we heard about the future developments in high aspect ratio and high dot density components. And in the second blog about laser welding in mobility, in general, I saw great interest in copper and other reflective materials. That is seems to be the trend for now. Also the similar material welding, also the cracking sensitive materials. We saw the dynamic beam laser approach from Civan lasers, the oscillating laser beam welding, both in TWI and also in the field cars welding. And then Paola also mentioned the short pulses preliminary results, that they could be a solution in this kind of welding applications. Civan also mentioned the parts that should keep low porosity as a challenge in this kind of applications. And then Paola mentioned how, well, it's important to keep the quality in the volume in battery packs production, how to produce volume batteries with good quality welds. So I think all these challenges summarize the discussion today. So I would like to thank again all of our speakers. Thank you very much for those interesting presentations. Also, thank you to our sponsors today, to FIX, to ficontec, and also to Acktar coatings. Thank you very much. And we are going to stop now the recording for the YouTube channel. And we can continue the discussion if there is any comment.